In this next set of videos, we're going to be working towards constructing examples of Galois field extensions. And so the first theorem that we're going to need for this is the following, which I sometimes refer to as the Goldilocks theorem, because it helps us get an idea about the size of a Galois group, or a Galois field extension. So the theorem says this: suppose that f and e are fields, f is contained in E, and little f is a polynomial in f adjoined x. Let's write omega for the set of roots of the polynomial f that happen to lie in the field E. The first part of the theorem is that if sigma is an element of the Galois group of E over f, then sigma of alpha also belongs to omega. So this is saying that the Galois group of E over f is permuting the elements of omega, it's shuffling them around. And the second statement of the theorem is that if f is an irreducible polynomial and E happens to be the splitting field for some other polynomial g in f adjoined x, then for all members alpha and beta and omega, there exists an element of the Galois group of E over f that carries alpha to beta. This is sometimes called a transitive action. We say that the Galois group of E over f acts transitively on the set omega. The reason we call this the Goldilocks theorem sometimes is that the first condition is somehow telling us that Galois groups are small. They're small enough that they have to take roots of the polynomial f to roots of the polynomial f. So where something can get mapped under sigma is quite restrictive. But the second statement is kind of on the other hand for that. It's telling us that the Galois group is large enough that amongst all the different elements of omega, alpha and beta, I can guarantee that there will be a member of the Galois group carrying one to the other, so long as the polynomial is irreducible. So that's giving us a lot of freedom in how we're going to move these roots of this polynomial around. So this is kind of a weight and a counterweight, if you will. The Galois group can't be too large, but it also isn't that small. Now let's get on with the proof of this. This proof is the first part. The first part is fairly straightforward. What we're going to do is we're going to take the polynomial f and write it as a sub n x to the n, so on and so forth, a1x plus a naught, where each of the a sub i's lies in the ground field f. Then 0 is a member of the ground field automatically. It's the additive identity. So it's fixed by sigma whenever sigma belongs to the Galois group. So 0 is sigma of 0. And 0, by assumption, is f of alpha. So the first two equal signs here are just sort of plugging things in. Now the next thing that we're going to do is use that sigma is a field automorphism. So because sigma is a field automorphism, we can plug in what f is equal to from the first line, and we can distribute the sigma, so to speak, across all the additions and take out all the powers. So we get that 0, which is sigma of f of alpha, is equal to sigma of a sub n times sigma of alpha, all raised to the nth power, and so on and so forth, plus sigma of a1, sigma of alpha, plus sigma of a naught. Now, because sigma belongs to the Galois group of E over f, we know that sigma acts as the identity on all things that belong to f. In particular, the a sub i's belong to f, and so sigma of a sub n is just equal to a sub n, sigma of a sub 1 is equal to a sub 1, and sigma of a naught is equal to a naught, and so on and so forth. So that brings us from the first line to the second line. And then we use the fact that what we're looking at right there is just the polynomial f evaluated at sigma of alpha. So through this long string of equalities, we have that 0 is equal to f of sigma of alpha. So when I evaluate the polynomial f at the field element, sigma of alpha, I get 0. And that tells me that sigma of alpha belongs to omega. So that's the first part of the theorem, the statement that elements of the Galois group of E over f map roots of the polynomial f to roots of the polynomial f. We're now going to move on to the second statement that says if we now assume that f is irreducible and E happens to be the splitting field for some other polynomial g in f adjoined x, then we can find an element of the Galois group of E over f that carries alpha to beta. So for the proof of this, let's suppose that alpha and beta belong to omega. And because f is irreducible, we can use our theorem from last time to take the identity map on the field f and extend it to an isomorphism from f adjoined alpha to f adjoined beta. This is something that we did in the slides on algebraic extensions. And let's call this map phi. Now, the polynomial g, what we assumed was that it lived in f adjoined x. F is a subfield of f adjoined alpha, so we can think about the polynomial g as living in the polynomial ring f adjoined alpha adjoined x, and similarly we could think of g as living in f adjoined beta adjoined x, and both of these fields are contained in E. So note that E happens to be the splitting field for g, even when we kind of view g as a member of these larger polynomial rings. It's because if g happened to split somewhere smaller, then g, when thought of as a polynomial in f, would split somewhere smaller. So E remains the splitting field for g even when we view g as a member of these larger polynomial rings. And what do we have? We have a map phi from f adjoined alpha to f adjoined beta. It maps alpha to beta, and it takes g to g because g actually happens to live in f, and we've extended phi from the identity map on f. So phi of g is equal to g, and splitting fields are unique. So we know that there's an isomorphism from E when viewed as the splitting field for g over f adjoined alpha to E when viewed as the splitting field of g over f adjoined beta. And so that's how we're going to go about building this member of the Galois group of E over f that carries alpha to beta. So note what's really going on here. We're trying to understand this connection that Galois sort of foresaw between field extensions and groups. And we've done some things before. In the past, we've known that if we have an irreducible polynomial in f adjoined x, and it happens to have degree n, we've seen previously that the degree of the field extension E over f is greater than or equal to n if E happens to be the splitting field for little f over f. This is in fact something we did on our last homework from algebraic extensions. And by this theorem that we just proved, we've shown that the same inequality is true for the size of the Galois group of E over f. So if we happen to have an irreducible polynomial, and we were working in a splitting field for that irreducible polynomial, there would be n roots of the polynomial in the splitting field. And what we've done is we've shown that I can take any root to any other. So if I fix a root, alpha, I have at least n choices for where I can send alpha under Galois group of E over f, and the second part of this theorem was asserting that I can find a different field automorphism for each of those choices. Now, the next thing I'd like to talk about is a normal field extension. So let's suppose that f is a subfield of E, both of them are fields. Then we'll say that E is a normal extension of the field f if two things are true. First of all, the extension has to be of finite degree, and second of all, the minimal polynomial of alpha over f needs to split in E adjoined x for every single element alpha in E. Now, that can be difficult to check. If we want to deal with normal extensions, which is something that we'll want to do, to go through and check that we have a polynomial splitting m sub f of alpha, one time alone can be hard enough, but then to check that that property is true for every single element of the larger field would be a disaster. So luckily for us, we have a theorem that gives us an easier condition to check. So here's the theorem. Suppose that f is a subfield of E, then E is a normal extension of f, or is normal over f, if and only if there exists a polynomial little f in f adjoined x, such that E is the splitting field for little f over the ground field f. So if we can show that E is the splitting field for a single polynomial over the ground field, and it doesn't even have to be an irreducible polynomial, then we know that we have a normal extension. And so this is going to be a really powerful theorem, and that's how we're going to use it. We're going to use this theorem to show that we have a normal extension by just looking at one polynomial instead of looking at infinitely many polynomials. Just as a quick example before we get started with the proof of the theorem, if you go back to the example we did earlier in the slides with the field E being Q adjoined the fourth root of 2, then this E is not normal over the ground field F, since the fourth root of 2 is an example of an element that lives in the field E, and we have figured out what the minimal polynomial for this alpha is. The minimal polynomial over the rational numbers of the fourth root of 2 is x to the fourth minus 2. However, we showed previously that this polynomial does not split in E since it only contains two roots of that polynomial, the real fourth root of 2 and negative real fourth root of 2. All right, let's get started with the theorem. So what are we proving? The easy direction first. First, let's assume that E is a normal field extension of F. Then by assumption, by definition of a normal extension, we have a finite degree extension. And what that means is that we can find an F basis for E, and let's put a name for that set. Let's name it S, and let's list out its members as alpha 1, alpha 2, all the way out through alpha n. And what we want to show, what we want to do is find a polynomial with coefficients in the field F that for which E is the splitting field. So the polynomial that we want, it turns out, is the product, as I goes from 1 to n, of the minimal polynomials of F over alpha I. So definitely not an irreducible polynomial. It's clear because each of the polynomials we're multiplying together, the m sub f of alpha i's, each one of them has coefficients inside the field F, and so their product F has coefficients inside capital F. And as E is a normal extension, we know that this polynomial F splits in E adjoined X. We're assuming that we have a normal extension. Each of the alpha i's belongs to E, and so their minimal polynomial will split inside E by normality of the extension. Hence, if we write K for the splitting field of little f over F, then K is going to be contained in E. If each of these pieces, m sub f of alpha I, if each of those terms splits in E, then this whole polynomial F splits inside of E. However, we can get the other containment. We can get that E is actually a subset of K because each of the alpha i's belongs to K. The alpha i's are the roots of the polynomials. Well, the alpha i's are some of the roots of the polynomial F, and so they will belong to the splitting field K. And of course the field F will belong to K. And therefore, the vector space that we can generate by F and each of the alpha i's, which is E, will be contained inside that splitting field K. So we've shown K is contained in E, and we've shown that E is contained in K, and the two must therefore be equal. So E is the splitting field for little f over F, and that's one direction of the theorem. For the other direction, I just want to do two little reminders before we start on the proof that will hopefully clarify things for you, because this is the hard direction. So I want you to remember that if K is a field and F is a polynomial in K adjoined X, then the splitting field for little f over K is given by K adjoined omega, where omega is the set of all roots for F. So one way that we can build the splitting field for a polynomial, at least in perhaps an unhelpful way, is we can take the ground field we're working with and we can just adjoin all the roots to it and look at the smallest field generated by that, and that is the splitting field for the little polynomial, for the little f over the ground field. And the next reminder is this. We know that splitting fields are unique up to isomorphism, but what I want to say here is a little bit stronger than that. If K is a field contained in L, and F is a polynomial in K adjoined X that happens to split inside the field L, then we can look for a splitting field of the polynomial F contained in L. And when we do that, that splitting field will be unique, not just up to isomorphism, but that splitting field for little f over K contained in L is unique. And that's not just up to isomorphism, that's just totally unique by the previous fact. So if we're working within L, then we take the field K and adjoin all of the roots of that polynomial, we're going to get a unique field, not just up to isomorphism, but just outright unique. So now let's start on the proof of the other direction. We're going to assume that E is the splitting field for the polynomial little f that lives in capital F adjoined X. And what we want to show is that E is a normal extension. It follows, because of the fact that E is a splitting field for little f, that it has finite degree. That's one of the first things that we need for a normal extension. That was actually a homework problem that you had from the algebraic extension section. So the rest of what we need to show is we need to pick an arbitrary element of the field E, and we need to show that its minimal polynomial over f splits inside of E. So here's what we'll do. Let's write G for the minimal polynomial of f of alpha, for alpha an arbitrary element in E. And let's define L. We can take this polynomial g, it has coefficients inside f, but f is contained in E, so we could think of the polynomial g as living inside of the field, or inside of the ring E adjoined x. So what we'll do is we'll define L to be a splitting field for g over E. And what we want to do is we want to show that L is actually equal to E, that we don't have to go any higher than E in order for the polynomial g to split. So let's define omega to be the set of all roots of the polynomial g that live in L. In order for g to split in E adjoint x, it's sufficient to show that omega is contained in E. And that's by our reminder from the previous slides. So let's let beta be an element of omega. And by our earlier theorem, we know, since g is irreducible, it's a minimal polynomial, we know that there's an element sigma in the Galois group of L over F that sends alpha to beta. Now what we want to do is we want to use that sigma is really a field automorphism. So beta is sigma of alpha, that's how we've picked sigma, and it's going to belong to the field sigma of E, whatever field that may be. As sigma is a field isomorphism, and E is the splitting field for little f over f, all of those properties are going to be carried over to the image of E, sigma of E. That is, sigma of E ought to be the splitting field for sigma of f, sigma of little f, over sigma of capital F. But we have that sigma of capital F is equal to f. That's because sigma is an element of the Galois group of L over f. So sigma is an F isomorphism. And because little f has coefficients in F adjoint x, sigma of little f is equal to little f as well. And because splitting fields are truly unique when you're working inside of a larger field, both E and sigma of E are subsets of L, we conclude that sigma of E is equal to E by the uniqueness of splitting fields. That is, sigma of E needs to be the splitting field for sigma of f, and sigma of f is f. And so E is also posing as the splitting field for little f over f, and because E and sigma of E are both subfields of the field L, we get that they're really and truly equal. Now, the last thing that we want to cover in these slides before we take a break is the idea of a separable polynomial. And we've discussed this before, but I'll just remind you of the definition. An irreducible polynomial f in f adjoint x is separable over the field f if f has distinct roots. And a polynomial is said to be separable if each of its irreducible factors has distinct roots. So the first definition is for an irreducible polynomial. An irreducible polynomial is separable if it has distinct roots. In general, we'll say that a polynomial is separable if each of its irreducible factors does. Now, if f is contained in E and both f and E are fields, we will say that E is a separable extension of f if the minimal polynomial of alpha over f is separable for all alpha in the larger field E. Now, the thing that's nice for us is that we've made this definition of a separable polynomial, but we're really interested in the case where our field f is the rational numbers, and we have the following lemma: if f is a field of characteristic 0, then every polynomial in f adjoined x is separable over f. So it has distinct roots somewhere. Now here I'm not going to do the proof, we just did a rather large proof, and the proof of this is much easier. So I'm just going to give an outline of how the proof should go, and it's an exercise to fill in all the details. So the first step is to assume that f is irreducible and to write out an expansion for what the polynomial f is. The second step is to go back and take a look at the formal derivative f prime of x and argue that the degree of f prime of x is n minus 1. I mean, this is obvious to you if you're thinking of calculus and the rational numbers, but here is truly where you're going to use that the field of the characteristic is 0, so that you don't have any type of fancy cancellation and have something of smaller degree. If the polynomial f has a repeated root, then f primed of alpha should be 0, where alpha is a root of f. And what you're going to do is use the irreducibility of f to arrive at a contradiction for that. So this is, you're going to use the idea that when you're looking at the minimal polynomial or an associate of the minimal polynomial that it truly has the minimal degree where alpha is a root.